Do you think you understand the universe? Here's the truth. 85% of all matter that exists is completely invisible. Scientists built modern physics on it. They call it dark matter. The shocking part is that this might be the biggest scientific misconception of our era. What if decades of research have been chasing a shadow that never existed? Let me show you what Richard Feynman, one of the most brilliant physicists in history, would think about this. I'm Marcus Hale, an astrophysicist. I spent 20 years defending dark matter as absolute truth, until I asked Feynman's question, where's the evidence? 50 years of searching, billions spent. Particles detected? Zero. Today I'm going to show you why this pillar of modern physics might be built on sand, and why that matters for you to understand how science truly works. The problem that created this obsession is simple. In the 1970s, an astronomer named Vera Rubin measured something impossible. Stars at the edges of galaxies were rotating too fast. Take your hand now. Spin it in the air like a disk. Imagine your hand is an entire galaxy. What should happen? Stars close to the center, lots of gravitational mass, should spin fast. Stars on the edge, far from the central mass, should spin slowly, like planets distant from the sun that barely feel its pull. Basic physics, right? That's exactly how our solar system works. Mercury, close to the sun, completes an orbit in 88 days. Neptune, at the edges of the system, takes 165 years. The farther out, the slower. The math is simple. Gravitational force decreases with the square of the distance. All of Newton's calculations work perfectly here. Vera Rubin expected to see the same pattern in galaxies. She pointed her telescopes at spiral galaxies and started measuring, star by star, region by region, building rotation curves that showed orbital velocity as a function of distance from the galactic center. But that's not what the data showed. The stars at the edge were spinning too fast. So fast that they should have been flung into space billions of years ago, like stones from a slingshot. But they remained there, calmly rotating in orbit. Something was holding these stars, something invisible. The detail few realize is this: it wasn't just that they spun a little faster. The orbital speed remained practically constant, even at enormous distances from the center. Imagine Neptune orbiting the Sun at the same speed as Mercury. This violates everything we know about gravity. The calculations didn't add up. The visible matter, stars, gas, dust, didn't produce enough gravity to hold these stars. The difference was colossal. We're talking about 5 to 10 times more mass missing. Imagine calculating that a bridge needs 10 tons of steel, but you can only find 2. That was the scale of the problem. And the solution they chose? To invent invisible matter to fill the gap. The most fascinating part? It wasn't just one galaxy. It was every galaxy we measured. Hundreds of them. All showed the same impossible pattern. Stars orbiting faster than the gravity of visible matter would allow. The solution conventional physics chose was simple and disturbing at the same time. There must be matter we cannot see. Invisible matter, which emits no light, does not interact with electromagnetic radiation, but has mass and, therefore, gravity. Think about what they are proposing. There is a substance that permeates the entire cosmos. It reflects no light. It absorbs no light. It emits no radiation at any wavelength. You cannot touch it. You cannot see it. You cannot detect it with any optical or electromagnetic instrument. The only way we know it exists is by the gravitational pull it is supposed to exert. This phantom matter would be spread throughout the universe, forming giant halos around galaxies, not just a little of it. 85% of all matter in the cosmos would be made of this mysterious substance. Everything you see, stars, planets, galaxies, nebulae, yourself, represents only 15% of the total matter in the universe. The Milky Way, according to this hypothesis, would be enveloped in a giant sphere of dark matter. This sphere would extend far beyond the visible stars, maybe 10 times the diameter of the galactic disk. And you're inside it now. Dark matter particles would be passing through your body at this very moment, trillions of them per second, leaving no trace. Stop now and think about what that means. 85% of the universe made of something we've never directly detected. Something that only exists because the numbers don't add up. That's dark matter. And since the 1970s, it's become scientific consensus. Now let me introduce Richard Feynman to the stage. Feynman was a genius. He won the Nobel Prize in Physics in 1965 for his work on quantum electrodynamics. He decoded quantum mechanics in ways no one had before. But what made him special wasn't just his intelligence, it was his brutal intellectual honesty. Feynman had a sacred principle he repeated in lectures and books. Don't fool yourself, and you are the easiest person to fool. This phrase summarizes his entire scientific philosophy. He knew that scientists are human. We have egos. We have favorite theories. We want to be right. And this desire to be right can blind us to the truth. He hated it when scientists defended theories without solid evidence. When someone presented a brilliant hypothesis, but without concrete data, Feynman would ask, "Where is the experiment? Where is the measurement? Show me." There's a famous story. A student presented Feynman with an elegant theory about some quantum phenomenon. The math was beautiful. Everything fit perfectly. Feynman listened and then asked, "Does it agree with experiment?" The student replied, "We haven't done the experiments yet, but the theory is so elegant it must be right." Feynman looked at him and said, "It doesn't matter how beautiful your theory is. It doesn't matter how smart you are. If it doesn't agree with experiment, it's wrong." That was the essence of Feynman. Experimental evidence above all else. Mathematical beauty is wonderful, but nature doesn't care about our equations. It just is. He used to say it doesn't matter how elegant your theory is. It doesn't matter how smart you are. If it doesn't agree with experiment, it's wrong. Period. The fundamental point is, dark matter is exactly the kind of hypothesis Feynman would challenge without hesitation. Why? Because dark matter was born from a mathematical deficit, not an observational discovery. We predicted how much mass should exist based on the laws of Newton and Einstein. We observed that there isn't enough mass. So we invented invisible matter to fill the gap. That is not empirical science. That is adjusting reality to fit the theory. Feynman would ask, "Are you creating an invisible and undetectable entity just because your calculations don't add up? Is this physics or faith?" And he'd be right to ask. Let's go further back in time and see how this idea gained traction. The concept of dark matter didn't start with Vera Rubin. It was first proposed in 1933 by an astrophysicist named Fritz Zwicky. Zwicky was studying the Coma Cluster, a massive group of galaxies 300 million light-years away. Zwicky measured the speed at which these galaxies moved within the cluster. Just like Rubin would do decades later, he discovered a problem. The galaxies were moving too fast. The gravity of the visible matter wasn't enough to hold them together. He calculated that there should be about 400 times more mass than we could see. Stop right there. 400 times. Not 10% more. Not double. 400 times more missing mass than everything we can see. It's like weighing an elephant and finding out the scale shows the weight of an anthill. Zwicky coined the term dark matter to describe this missing mass. But at the time, it didn't catch on. Most physicists ignored it. They thought Zwicky was wrong, or that there were other explanations. The hypothesis lay dormant for decades. Until Vera Rubin. In the 70s, she brought irrefutable data from spiral galaxies. And this time, the scientific community paid attention. The numbers were too consistent to ignore. The problem was real. And the proposed solution was to resurrect Zwicky's dark matter. The crucial point, dark matter wasn't discovered, it was inferred. We have never seen a particle of it. We have never measured its presence directly. What we did was create computer simulations showing that if you add giant halos of invisible matter around galaxies, the rotation curves fit perfectly. Think about that for a moment. Do you see the problem? It's circular reasoning. First, we predict how much mass must exist based on laws we assume to be correct. Second, we observe that there isn't enough mass. Third, we invent invisible mass so the prediction works. Fourth, we say the prediction was right because we invented the mass. It's like predicting there should be 10 apples in a basket, finding only 2, adding 8 imaginary invisible apples, and then declaring that your prediction was perfectly right. Feynman would say, "Wait a second. Are you telling me that 85% of the universe is made of something you've never detected? Where's the particle? Where's the interaction? Where's the direct evidence?" And here we reach the heart of the matter. 50 years of searching. 50 years of incredibly expensive experiments. And how many particles of dark matter have we detected? 0. None. Not a single one. Experiments like LUX, Xenon, and others were built deep underground to avoid cosmic interference. Why underground? Because cosmic rays from space constantly bombard the surface, creating noise in the detectors. So we built laboratories miles underground in abandoned mines, protected by layers and layers of rock. These detectors are incredibly sensitive. Giant tanks filled with ultra-pure liquid xenon. When a particle interacts with a xenon atom, it produces a tiny flash of light. Sensors capture this flash. If a dark matter particle passes through the detector and collides with a xenon nucleus, even if it's an extremely weak collision, we should see the signal. The experiments ran for years. Decades of accumulated data. Hundreds of scientists analyzing every event, filtering out noise, searching for the characteristic signal that would indicate a dark matter particle. Result? Nothing. Absolutely nothing. Not only that, each generation of detectors gets more sensitive. The Xenon 1T had 1 ton of liquid xenon. The next, Xenon NT, has 8 tons. Greater sensitivity, more collection time, and still, no confirmed detection. Every experiment that fails to detect dark matter narrows down the space where it could be hiding. Here's what this means in practice. Each experiment places tighter limits on where dark matter could be. The parameter space, the range of possible masses and interactions, shrinks year after year. It's like searching a room for an invisible elephant, and each year we say, it's not under the bed, it's not behind the curtain, it's not in the closet. At some point you have to ask, what if there's no elephant? Now, absence of evidence is not evidence of absence, right? That's the standard argument. Just because we haven't found it yet doesn't mean it doesn't exist. And that's true in science. But when you're looking for something that supposedly makes up 85% of the universe, and you can't detect a single particle in 50 years, you have to start asking questions. If dark matter is everywhere, why is it so hard to find? If it dominates the cosmos, why is it more elusive than any other known particle? These are legitimate questions that Feynman would ask. The big twist. What if the problem isn't missing matter? What if it's wrong gravity? Let me introduce an alternative that few people know. Modified Newtonian dynamics, or MUND. In 1983, an Israeli physicist named Mordechai Milgram proposed something radical. What if Newton's law of gravity doesn't work exactly as we think on galactic scales? This is a bold idea. Newton's laws are sacred in physics. They worked for 300 years. They took man to the moon. They control satellites. They predict eclipses with second accuracy. You don't suggest Newton is wrong lightly. But Milgram realized something fundamental. We've never tested Newton's second law at extremely low accelerations. In the solar system, accelerations are relatively high. Earth experiences a gravitational acceleration of about 10 meters per second squared towards the Sun. Even Neptune, at the edge of the system, still has a measurable acceleration. But stars, at the edge of galaxies, they experience accelerations trillions of times smaller. Accelerations so small that we have never measured anything similar in a laboratory or in the solar system. Milgram's question was, what happens if the laws of physics behave slightly differently in these extreme regimes? It wouldn't be the first time. Newtonian mechanics works perfectly at normal speeds, but when you approach the speed of light, it fails. Einstein had to develop special relativity to correct this. Newton's gravity works perfectly for normal objects, but near black holes or in the fabric of space-time, it fails. Einstein developed general relativity. Perhaps, Milgram thought, there's another frontier where Newton fails. Ultra-low accelerations. Milgram modified Newton's second law just a little bit. He proposed that at very low accelerations, below a certain threshold, gravity becomes stronger than Newton predicted. Not much stronger. Just enough to explain why stars at the edges of galaxies rotate faster than expected. The surprising thing is that MUND works incredibly well. When you apply Milgram's modification to the rotation curves of galaxies, they fit perfectly. No invisible matter, no phantom halos, just a small change in the law of gravity. More than that, MUND makes predictions. If you measure the distribution of visible matter in a galaxy, MUND predicts exactly how it will rotate. And when we test this in hundreds of galaxies, Mond gets it right almost every time. Without adjusting parameters, without inventing different amounts of dark matter for each galaxy, just one law, one number, and it works. Compare this to dark matter. For each galaxy, you need to adjust how much dark matter there is, where it is distributed, what the halo density is. It's a model that you can twist and adjust until it fits any observation. Mond doesn't have that flexibility. Either it works, or it doesn't. And in galaxies, it works. So why hasn't the scientific community embraced Mond? Why is dark matter still the consensus? The answer is complicated, but I'll simplify. Because Mond has its own problems. Mond explains individual galaxies perfectly. But when you go to larger scales, galaxy clusters, large-scale structure of the universe, the cosmic microwave background, Mond starts to fail. It doesn't fit as well. Why? Because in galaxy clusters, the discrepancy between visible mass and gravitational mass is even greater than in individual galaxies. Mond solves part of the problem, but not all of it. You still need some additional matter, although much less than traditional dark matter requires. And then there's the cosmic microwave background, the remnant radiation from the Big Bang. The tiny fluctuations in this radiation tell us how matter was distributed in the early universe. Dark matter models predict these fluctuations with remarkable precision. Mond has difficulty doing the same without additional modifications. But the most famous challenge for Mond is the bullet cluster collision. In 2006, astronomers observed two galaxy clusters that collided with each other. Imagine this: two giant swarms of galaxies, each containing hundreds of them, colliding at millions of kilometers per hour. What happens? The hot gas between the galaxies collides and decelerates, creating a massive shockwave. But the galaxies themselves, tiny objects separated by vast distances, pass through each other like bullets through a fog. They don't collide. Scientists used gravitational lensing, the bending of light by gravity, to map where the mass is located in the post-collision system. This is an elegant trick. Light from distant galaxies behind the cluster is bent by the cluster's gravity. The amount of bending reveals where the mass is. And they discovered something fascinating. Most of the gravitational mass was not where the gas was. It was where the galaxies were. There was a clear separation between the highest concentration of visible normal matter, the gas, and the highest concentration of gravitational mass, invisible, but detectable by gravitational lensing. This was hailed as definitive proof of dark matter. The interpretation is straightforward. The dark matter halos around the galaxies passed right through the collision without interacting, like ghosts through walls. Normal gas, being normal matter, collided and decelerated, lagging behind. Therefore, gravitational mass is separate from visible matter, proving that invisible matter exists. Many physicists consider this the nail in Mond's coffin. How do you explain gravitational mass separate from visible matter without invoking invisible matter? Mond modifies gravity, but it doesn't create mass out of nowhere. Mond struggles to explain this without invoking some form of additional matter. And that's why many physicists consider the bullet cluster to be the definitive refutation of Mond. However, there's a nuance few mention. Mond can still explain the bullet cluster if you add some additional matter, just far less than traditional dark matter requires. And there are relativistic versions of Mond that attempt to solve these larger-scale problems. None are perfect yet. The point is, neither Mond nor dark matter perfectly explain everything. Mond dominates in individual galaxies. Dark matter fares better on cosmological scales, but only if you constantly adjust parameters. And remember, no dark matter particle has been found. So what's the right answer? Perhaps neither. Perhaps we are witnessing new physics that we don't fully understand yet. Perhaps gravity needs a more profound revision than Mond. Perhaps exotic matter exists that isn't the type of dark matter we're looking for. What matters here isn't choosing a side. What matters is recognizing that we are facing a genuine mystery. And when you are faced with a mystery, you cannot simply choose the most convenient explanation and stop questioning. Here's what Feynman teaches us. He had a famous phrase that sums up his entire philosophy. I would rather have questions that can't be answered than answers that can't be questioned. Think about what that means. Unanswered questions are opportunities. They tell you where physics is incomplete, where discoveries are waiting, where you need to work harder, think deeper, do better experiments. But answers that cannot be questioned, that is dogma. and dogma kills science. When you declare something to be true just because it solves a mathematical problem without direct experimental evidence, you stop looking for alternatives. You stop asking questions. And science dies. When Feynman didn't understand something, he didn't invent invisible explanations to fill the gap. He admitted ignorance. He said, "We don't know yet," and that's the strength of true science. There's a famous lecture Feynman gave on the nature of science. He said, "I can live with doubt and uncertainty. I think it's much more interesting to live without knowing than to have answers that might be wrong." This was his fundamental philosophical stance, but dark matter has become dogma. Question it publicly and you are marginalized. Suggest alternatives like monde and you are ridiculed. Feynman would fight against this. Why? Because a hypothesis that depends on something undetectable cannot be treated as established truth. Feynman would say, you have a hypothesis that depends on a substance that has never been detected, that makes up most of the universe, and that you can freely adjust to explain any observation. And you're telling me that this is the only acceptable answer? Where is the scientific humility? Science does not advance by consensus. It advances by evidence. And to this day, direct evidence for dark matter is zero. We have indirect evidence, things we don't understand and attribute to invisible matter. But indirect evidence is not proof, it's inference. And when inference is based on laws that may be incomplete, like Newtonian gravity on galactic scales, you cannot call that established truth. You have to call it what it is, a working hypothesis. The danger of consensus without evidence is that it freezes progress. When an idea becomes orthodox, we stop seeking alternatives. Resources flow to confirm the dominant hypothesis, not to rigorously test it or explore competing explanations. Here is something we rarely admit. Billions of dollars have been poured into dark matter detectors for decades. Think about what that means. Giant underground laboratories, detectors the size of buildings, hundreds of physicists dedicating their entire careers to searching for these particles. All of this based on a hypothesis that has never been experimentally confirmed. Meanwhile, alternatives like monde receive a tiny fraction of the funding. Few research groups work on it. It's hard to publish papers on monde in prestigious journals. Young physicists are advised not to work on it if they want stable academic careers. Why? Because it goes against the consensus. It's as if we put all our chips on a horse that has never reached the finish line, while ignoring the other horses in the race. And when someone suggests that maybe we should bet on another horse, the response is, no, this horse will win eventually. We just need more time and more money. That is not the scientific method. That is an emotional commitment to an idea. And Feynman would hate that. Dark matter might exist. Maybe we just haven't detected it yet. But treating an unconfirmed hypothesis as truth is dangerous. It's unscientific. And Feynman would fight against it, claiming that 85% of the universe is made of something invisible, undetectable, that we only know through indirect inference. That's an extraordinary claim. And 50 years without a single particle detected? That's not extraordinary evidence. The universe doesn't owe us easy answers. Reality is stranger and more complex than our minds can easily imagine. Maybe dark matter is real, and we're just using the wrong detectors. Maybe monde needs refinement or extension to explain large-scale phenomena. Maybe it's something entirely different, a deeper modification of general relativity, or exotic physics we haven't even conceived of yet. The history of science is full of moments where the consensus was wrong. For centuries, everyone believed the universe was eternal and unchanging. Even Einstein added the cosmological constant to his equations to keep the universe static, because the idea of an expanding universe seemed absurd. Then Edwin Hubble measured galaxies moving away from us, and the entire consensus crumbled. For centuries, physicists believed that time was absolute, the same for everyone in the universe. Newton built all of mechanics on that assumption. Then Einstein showed that time is relative, that it can dilate and contract depending on speed and gravity. The consensus was wrong. For decades, physicists believed the conservation of parity left-right symmetry was a fundamental law of nature. Then experiments showed that weak nuclear forces violate parity. The consensus was wrong. The point isn't that the consensus is always wrong. The point is that it can be wrong. And we only find that out when we question it, when we test it, when we keep an open mind to alternatives. But we cannot stop questioning. We cannot accept invisible explanations just because they make the numbers work. We cannot confuse mathematical convenience with physical truth, and we cannot treat unconfirmed hypotheses as established facts. Feynman taught us this. The value of science isn't in having answers. It's in asking the right questions, in looking at the unknown and saying, I'm going to investigate this honestly, without defending pet theories. The stars spinning at the edges of galaxies are telling us something profound about the universe. They are showing us that we don't fully understand gravity or matter or both, and that is wonderful. It's an open window to new physics, whether it's dark matter, modified gravity, or something completely different that we haven't even imagined yet. There is something profound waiting to be discovered, a fundamental piece of the cosmic puzzle that we are missing. And the only way to find it is by being honest about what we know and what we don't know. And here's the question that matters. Are we being honest? When we say that 85% of the universe is dark matter, are we communicating certainty or inference? When we teach this in textbooks, are we making it clear that it's a hypothesis or presenting it as fact? Are we demanding enough evidence before declaring victory? Is 50 years of fruitless searching enough to reevaluate? Or are we going to keep saying, just one more decade, just one more experiment? Are we open to being surprised? If a young physicist showed up tomorrow with a radically different theory that explains the observations, would we be receptive? Or would we have so much emotional and financial investment in dark matter that we would reject the alternative without fair consideration? These are the questions Feynman would ask. And they are uncomfortable questions because they expose our human weaknesses. We want to be right. We want our years of hard work to mean something. We want the particles we're looking for to exist. But nature doesn't care about what we want. If Feynman were alive today, he would be asking for more data, questioning assumptions, exploring alternatives, and comfortable saying, I don't know, and that is wonderful, because science lives in the I don't know. That's where discoveries happen, where paradigms shift, where we find truths stranger and more beautiful than anything we could have ever invented. The next time you hear that 85% of the universe is dark matter, ask Feynman's question. Where's the evidence? Stay skeptical, demand solid evidence, and never accept answers that can't be questioned. If you want to think like Feynman, question honestly, embrace the mystery, challenge the consensus, subscribe to the channel. Every week, I bring you physics that proves why doubting is a beautiful thing. Leave a comment. Do you think dark matter is real, or are we just chasing shadows? I want to hear your perspective. Until next time, keep questioning.